Okay, go ahead.
Okay, let me introduce that good morning U.S. participants, and a good evening to the participants in Asia, and a good afternoon to our European attendees. I'm organizer and moderator of this session, and I'm an emeritus professor from the Department of Stat and Data Science at Korean National Open University. So, the theme of our session S35. Let me share my PPT slider. So Lynne's slide, share what I'm doing. Yeah. Please let me share my slide.
Yes,
Can I interrupt, Karen? Can you see my screen?
Explain by okay. And the theme of our session S35 is pioneering women in statistics and data science, bridging global research and innovation. It is an honor to welcome 3 distinguished scholars from US, Europe, and Asia to join us today. I hope we can have a very productive and fruitful time and a happy time. Let me introduce first the speaker, Lynne Billard. Is very famous from the University of Georgia. Why not give a big hands, Welcome to Big Hands. Would you start, Lynne? Would you start your presentation, okay?
Yeah, my question is, can you see the screen? I can't seem to get it. I've got it on. I can see it, but can you see it?
Yes, we can. Thank you.
You can see it?
Yes, we can.
Okay. We can see the slide.
Okay, thank you. Well, that's all right. Okay, so thank you for inviting me. I'm happy to be here. I don't want to say too much about my career. There's too much has been written about it. You can read it online, especially the conversation. Well, that was 10 years ago now in statistical science, but I haven't done much else since then. But I just got a couple of slides on my career. I started out at the University of New South Wales in Australia, and I had 2 very important things. I had a mathematics cadetship, and it was the only year that they gave any cadetships to women, and there were 3 of us, and we actually outdid the men, but that's another story. And the other person was my mother, who was insistent that we all go to college, whether we could afford it or not, and we couldn't afford it. But the cadetship meant that I could pay for myself. So I worked there. I got my degree. I worked for them for 3 years, taught for them for 3 years. That was the condition of the cadetship. And during that time, I did my doctoral degree simultaneously. Then I go off to England, and I've been in many different places. I've worked in a lot of different areas. Probably the most significant work was the incubation period of HIV and AIDS. And then I came here to Georgia a number of years ago to, quote, change everything. And my advice to young people, if they're watching, is use the opportunities that are offered to you along the way. One example for me was that I was put on the Census Advisory Board at the end of the 90s. There were a lot of controversies over sampling. It took me to Alaska as an observer. I've traveled the world in all sorts of places, using my job as a vehicle for seeing the world. And probably the most important one was my visit to Slovenia. And the next speaker, I believe, was the key person. I think she's next, Anuška Ferligoj. She was the catalyst that got me into symbolic data. It's an interesting story. I'll let her tell it if she wants to. Anyway, I did, as a result of visiting Slovenia, get into symbolic data. And so that's what I want to talk about. And so very quickly, I want to look at the present. And if I've done that page correctly, you can't read it. It's too dense to read. And that's what the modern data sets are like, or a lot of them. So we have to do something. And so let me just put it in perspective. Classical data are single points in p-dimensional space, but symbolic data are hypercubes or Cartesian products in p-dimensional space. So you might, an observation, you aggregate a massively large data set into categories or classes, and you finish up with a list, or you finish up with an interval of values or histograms. Histograms can have all sorts of weights. The one we're all familiar with is the histogram with relative frequencies, but there are lots of other weights that come out of computer science that are actually quite important. But symbolic data are different from classical data. It's not just a hypercube in p-dimensional space. There are other things that are going on. And so I want to look at 3 or 4 particular scenarios to say why you have to look at symbolic data, analyze it differently. Most of the time, people just take classical surrogates. They take an interval and take the midpoint, for example, and analyze those midpoints. If you look at this trivial example, we've got an observation weight. A classical observation, say you measure somebody, the weight is 135 pounds, and this, you've got a sample of size 1, so we know that the sample variance is 0. But if you have a single observation, for example, 132 to 138, the sample variance is actually 3, not 0, if it's the interval. And for this interval, it's 12. And yet, in all cases, the midpoint is 135. And if you are analyzing all those midpoints, you don't get the right answer because you're losing the internal variation. And you can, so this is what I just said. If you take the interval midpoints, you don't use the entire information. In fact, you can show that the total variation is the within plus the between. And the between is from midpoint to midpoint to midpoint. I'll just talk in terms of intervals. I do have a scenario later for histograms. And when you use classical surrogates, all you're using is this between variation. You're just totally ignoring the within variation. And it's the within variation that gives you this 3 and this 12. And there are a bunch of general books and references that you can look on this. Okay, so as I said, I've only got a few minutes. I'm going to look at 3 or 4 scenarios, basically showing you the difference between using a classical surrogate and using the symbolic analysis. In other words, using the entire interval if we have interval observations. If you don't remember principal components, that's all right. What you do is you have a bunch of observations. You calculate a principal component, which is a linear combination of the observation and the eigenvalues, the eigenvectors, and then you have these conditions. And the key thing is that you calculate the variance covariance matrix, and then you project the observation onto principal component space. Okay, so when you calculate the variance covariance matrix, of course, you've got these variations, and you can either do it using, this is the formula, using the entire interval, calculating the variation. So doing it this, a student of mine, Jennifer Lee Rademacher, a number of years ago, we could calculate the exact covariance matrix because we had the exact covariance formula. And I say exact, using the entire interval, not just the midpoints. And then, so you got out the exact eigenvalues, eigenvectors, and the exact principal component, and then you had the visualization. So your observation now is a hypercube in space. instead of a single point. Okay, this is just a three-dimensional version. And the projection into the principal component space here, it's easier to see here. And this shaded purple is the actual projection on the hypercube, the data point. And you can see that this is a polytope. And so Jennifer Lee Rademacher, she came up with a method to measure the exact boundaries here. Previously, people had just been using these heavy black lines, and so you've got a lot of space in here that looks like it's in the PC, but it's not part of, there's no data associated with it. So when we applied the analyses to a set of data, there's faces data, there are 6 variables. If you can read quickly, there's just face measurements. And then if you do the principal component analysis, you've got the polytopes, you can sort of see. Now, as it so happened, the 27 observations were in sets of 3. You had 3 observations from each face. And when you did it using a classical surrogate, I mean, you've got points in here, but here, the principle, using all the data, you've got the sets of 3 are obvious. The 3 black ones here overlap, the 3 red ones here overlap, but the 3 romas, you've got a face here, and a face here. Over here, you've got here, here, here. They're all over the place. In other words, when you're using the classical surrogates, you can't at all pick up that the data are in sets of 3, and they're just all over the shop. And it was just by accident that we had these data in sets of 3. So what do we have? Using all the information in the data set, we get a coherent and exact PCA. Using classical surrogates, we get wrong answers. We get answers, but they're wrong. A second anecdote is, and I've got more information on this PowerPoint page than you need, but we've got a bunch of data that are intervals. We model it as a regression, and we want to use these regressions to inform a partitioning into K clusters. For those of you who are into petitioning, you have some criteria. Doesn't matter if you don't understand, that's not the point of the talk. You do have to get some distance measures. And in this example, we looked at 3 distance measures between lines, between intervals, not between points. How we get those is another story, but you can get them. You have an algorithm. This is very standard. Basically, you have a formula in here for allocating a point into a particular partition or cluster, and this is published here. So, just one example. We have tons of examples. This is a simulation study. We've got 3 very different equations, so you can see them here. Those are the original data simulated. I think there were 3,000 observations. And the question is, can we recapture this using the algorithm? Now, classical observations, typically they'll use a version of k-means. So we'll just stick with k-means. And so you've got the original data. When you use k-means, either with the Hausdorff distance or the city block distance, you can see k-means is coming up with this here as one cluster, this is a cluster, and this is a cluster. Clearly not correct. Okay, you've got the original data here. The clusters are not picked up properly at all. When you do the regression-based clustering where we're using the entire interval, the original data, we started off with this initialization, very obviously different from what the real initializations are. After iteration 3, it's pretty good. Iteration 9, you can't do better. And we've recaptured the 3 clusters completely. completely and correctly. Why? Because we used all the information in the interval, not just the midpoints, not just the classical surrogates. And I go to computer science talks, and I'll talk with them about using all the information in the interval, and they'll always say, "Oh, the midpoint, that's enough, that's enough." It's not enough. You can see from these two examples already that you're not getting you're getting answers, of course, but you're not getting the correct answer when you just use a classical surrogate. Okay, here's an example for histogram clustering in deference to our chair who's from Korea. This was done with a student of mine who's back in Korea. And again, we're doing clustering, hierarchical clustering, based on histogram observations. You don't need this page, but what you want to do is to convert all the histograms into a common base. Again, just some notation for those of you who are into hierarchical clustering. But the real value here is we have a double algorithm. You partition by the means of the histograms, and then by the variances of the histograms, using the entire histogram, not the midpoints. And then a simulation here, we've got three different, we've simulated observations from three different bivariate normals. They're plotted here, and then they're aggregated into histograms. And then if you take the Brito and Chavant algorithm, 29 of the 1,000 were correct, but using the entire interval, all 1,000 are correct. So once again, it's a broken record, but using all the information in the interval, or in this case, a histogram, you will get the correct answer. And the final vignette is with time series. Here's some data from Dow Jones, min-max measurements daily. And what people, if you go into the economic literature, what they'll do is they'll fit a time series across the maximum points, fix a time series across the minimum points, and go from there. But using the center point and the range is exactly equivalent to using the min and the max of the interval. And again, I want to show you that it doesn't come out properly. There's some China temperatures high, min, max for the day or the month or whatever the case may be. But I want to come back and look at this. In time series, you have, supposing we've got this interval at time t and this interval at time t plus k. Now, in time series, what you do is you've got dependencies across time. The observations for t are dependent upon t plus k dependent on observations at t. But if you use just the min-max, you're saying you've got a dependence between the maximum here and the maximum there, and in the separate equation, the maximum here and the maximum and the minimum here and the minimum there. But in actual fact, take any point along the interval at time t, and it has a dependence to any point along the line t plus k. So you have to take into account these internal dependencies as well. So you don't just have dependency between the endpoints or the center range. You have to use dependencies completely throughout the intervals. So we did that. This is another student of mine. Again, if you're into time series, this is just an autoregressive of order p. There's the notation there. Don't worry if you haven't done time series and you don't know what that is, but the observations are intervals. Okay, the observations are intervals at time t. Okay, so earlier for the principal components, I gave you the formulas for the covariance between two variables x and y when the x and y were intervals. Now you can just extend this. Instead of x and y, you've got yt and yt plus k, and you adjust it, and you've got the autocovariance function for the entire interval. Then you can estimate the parameters. This rings a bell if you're into time series. And then again, just to show you in one simulation, there's a paper by Wang et al., which is a wonderful paper. And what they did is they took all the different methods that have been used, those that use the endpoints, those that use the midpoint and the range, the center range, those that did this, those that did that, the different papers or studies that used a classical surrogate, okay? And then they added something called the ST method. And their method was better than all the others. So all we had to do was to compare our method using the entire interval with Wang et al. And you can see what's happening. And the other thing we did is that across the interval, a lot of the work that's been done assumes that observations are uniformly spread across that interval. But we took uniform, we took triangular, we took Pareto, and we took a U-squared. And all four of the internal distributions gave pretty much the same result, these here. This one up here is this is the bias in this case, in this formula. This one here is the Wang et al., the ST method. And you can see again, using the entire interval is far better. The bias is a whole lot better for estimating the parameters. And likewise for the second parameter, this is a study with two parameters. And again, using the internal distributions doesn't make a whole lot of difference, which is interesting in itself, but it's clearly a whole lot better than using any of the classical surrogate methods. And I think that's where I'm going to stop, okay? I could go on, there's lots of examples, but the real point is you have large data sets, you have to aggregate somehow. You aggregate into intervals, for example, or you aggregate into histograms. But then when you analyze those intervals, when you analyze those histograms, you have to use the entire interval, the entire histogram, and not classical surrogates. Okay, I'll stop there.
Thank you, Lynne, for your very great presentation. Especially, very impressive to me, the visualization of your analysis process. It is easy understanding what you're doing. You know, can I have one question to you first? So what kinds of software to use symbolic data analysis nowadays?
Oh, well, some people have, most of the published software, it's on R, but virtually all of it uses classical surrogates. And so I've actually got someone working right now as we speak to try and get some of these methods up on the R platform so that you can do it properly.
Oh, okay. So is there any question?
You can use R. I've done it in SAS. Usually what I've done is I've used SAS and I have my student do it in R, and then we can compare answers.
So you can the programming by for the symbolic data analysis, right?
Pardon?
I mean that when we try to analysis symbolic data analysis process. So what kinds of software? So you can use the SAS.
You can use SAS. I mean the two books that I've written on symbolic. Every single example in that book, I wrote SAS code to analyze. But I've got students working on putting it up on the R platform.
Yeah. Do you have any question among the audience?
Yes, we have one question. It says, are there any clear connections between symbolic data analysis and probability theory? How to study some symbolic data analysis using asymptotic and similar tools? Are there any special issues to take into account? And what role do mathematical dimensions play? And that question goes on a little bit.
Yeah. Okay. So there are really two directions that future work need to follow here. One is, taking every statistical methodology that's been developed over the decades, century, and redo it for intervals for histograms, methodological work. The other direction is the mathematical underpinning. And that's your question, really, isn't it? And there are some papers. There are not a whole lot because the mathematics behind it is not trivial. A couple of my students, we've got papers on deriving the maximum likelihood estimation of the estimators involved with time series, involved with the time series one just came out last year, I think, or maybe it's this year, or the mathematical derivations, and the asymptotic theory of those mathematical formulas. The covariance and variance, there's been a few papers that have come out with some of my students. There's a group at New South Wales in Sydney, though, that I think are going to be important to the future here, because what they've got a bunch of papers that have come out that shows that if you start with the histogram, say, if you start with the interval and get your answers, that asymptotically, those answers go back to the original data for the, as though you had a manageable size data set instead of a massively large data set. And so that essentially is showing that developing results for histograms for intervals is the right way to go, because asymptotically they come down to where they should be.
Thank you. And any other question? No more? So Lynn have to go to her class.
I have to go to class. I'll stay for a couple of minutes, but I have to go to class. I'm sorry.
Okay, and thank you for your, and before her presentation, I would like to introduce her research and her career here. So her research focusing on like this, shortly I introduce. Can you see this slide? And also there are many books she published, So I have a symbolic data analysis, Lynn and Edwin together, And also, I'm very impressed to me that during a survey, the publication, past, present, and future academic women in mathematical science. It was very impressive to me there. And also, and next is so many awards she has. I cannot page down, page up, so many here, So it's a great honor for us to invite you to give us a talk and accept our invitation. Thank you.
Well, I'm honored to be invited. Thank you.
Thank you. Have a good time. Have a good day. And let me see. Oh, next speaker is Anuška, Professor Anuška from the University of Ljubljana, Slovenia. Her topic is clustering of attribute or network data. So she's an expert in clustering, and so many work and so many awards here. So scientific work is like generalized block modeling, and also the understanding large temporal network and spatial networks, or the network clustering and block modeling. So many very good book publication she has. So let us give a big hands to the Anuška. And so would you, let me share her slide, So 공유, 이걸 끝나야지. No more sharing, so yeah. So, Anushka, your slide here.
Okay.
You can control your slide, right?
Hopefully so.
Yeah, you can control your slide. First page, go up.
I don't see
Uh-oh.
how to do it. Sorry.
Uh-oh. So you can go first slide.
Sorry. Maybe I will share again. I don't know how to do this.
Oh,
Try
you cannot-
using the page up key
Page
to get
up.
to the top.
Like
Sorry,
this
what?
one.
Try using the page up or the arrow keys to get to the top of your screen.
Okay.
That looks better. Getting there.
Yeah.
Oh, the other direction. Yes.
Yeah. Right.
Okay, only I can't come. Just a second.
Full screen.
Wait a minute. Какво да
Oh
го
yeah, you can do it. Okay.
Top of that rectangle button.
Okay. Well, anyhow, thank you very much for inviting me, Professor Teirim. And I'm really honored to be together with my friend Lynne Billard. So it's still not okay. Okay. So Lynne, Teirim asked me to say something about me. I'm Professor Emeritus at the University of Ljubljana, otherwise Professor of Statistics. My research fields are mainly cluster analysis and social network analysis, but also many other topics. Beside my teaching activities and my research, I had two goals in my career. One is to organize statistical education in Slovenia. So I organized with my colleagues the first interdisciplinary doctoral program in statistics in 2002, and then later master programs on applied statistics at University of Ljubljana. And I collected all professors around the university to take part and teach in this program. The other goal was to connect academic statistics and official statistics. And that's why I was 15 years president of Statistical Council of the Republic of Slovenia. And I was also 5 years member of European Statistical Advisory Committee for Eurostat in Europe. So this would be in short about me, I will talk about the main path of my research work, which is around cluster analysis. And this will be introduction, but we will see. I have to go quickly, not to be late. So the title is about clustering attribute and/or network data. So let us define one and the other. I understand attribute data as a typical statistical data set, a multivariate data set, which means we have n units and m variables. Lynne was talking about that before. And then we have network data. Network data can be of many different kinds. I will say here the most simple definition of a network. A network is defined by the set of units and a relation. So here, this network is presented by a graph with nodes and links. Links can be directed, described here by an arrow, or they can be edges if the relation goes from first unit to the second and backwards. So this is a binary relation. So this is really the simplest possible definition of a network, but I will speak about this simple network in this talk. So cluster analysis is about grouping into clusters in such a way that units in a cluster are as similar as possible and according to selected variables, and units in different clusters are as dissimilar as possible. It's a very old problem. It is simple, it is understandable, but it is still quite an exciting activity. And the cluster analysis is used in many scientific disciplines, including artificial intelligence right now. Let us formally define clustering problem. Cluster analysis is known also as classification or taxonomy. So the problem is, given a set of units, determine subsets, which are clusters, that are homogeneous and or well separated according to the measured variables. The set of clusters form clustering. It can be partition, it can be hierarchy, it can be many different definitions of it. Then the problem, the clustering problem can be formulated as an optimization problem, where we want to determine clustering C star for which, minimizing the criterion function over the set of feasible clusterings. The criterion function is this P. So we have criterion function and the set of feasible clusterings here. Let me just say a little bit about possible criterion function in this general or classical cluster analysis. It is usually a function of the similarity measures that we select according to the problem that we have. If we have a partition into K cluster, then, for example, Ward criterion function can be defined, which is this. For each unit in a cluster C, we calculate center, and then we calculate the squared Euclidean distance from each unit to this center. We sum up inside the cluster, and then we sum up across the clusters in the clustering. So this is a typical Ward criterion function that is usually used, a kind of variance stuff. For a finite and non-empty set of units, the set of feasible clusterings is also finite. So clustering problem always, the solution exists. Since the set of feasible clusterings is usually very large, it is not easy to find the optimal solution. In general, it is an NP-hard problem. So therefore, several heuristic algorithms have to be used as hierarchical, local optimization, k-means, and so on. Also, Lynne mentioned some of them. What is the benefit of the optimizational approach? Actually, here we have two things that we can adjust to the clustering problem. One is the criterion function. The criterion function can be defined according to the problem that we are going to solve. And we can also specify the set of feasible clusterings according to the problem that we have. Classical clustering deals with clustering of only attribute data. Block modeling is searching for clustering of units according to the network data only. And here, an appropriate criterion function has to be defined. But we can also cluster attribute and network data. In this case, the attribute data are treated by the criterion function. And the set of feasible clusterings is defined with the network data. And I will say something about both of these approaches, block modeling and clustering of attribute data. let me say something about block modeling. The goal is to reduce a large network to a smaller structure. Let us look to the picture on the right. So on the top, we have a network. This is student government of University of Ljubljana. We have prime minister, ministers, and advisors. And on this data, we use one of the block modeling procedures, okay? But I will talk about that later, these procedures. And we obtain 4 clusters: the blue one, the yellow one, the green one, and the pink one, right? Let us see what are the characteristics of this cluster. The blue one is connected only to the yellow one on both sides. The pink one has arrows, you know, so they are related. This is advice relationship, only to the yellow and only to the green. It's directed one. And the green one gets the arrows from the pink one, but they are in both ways connected also with the yellow one. So here down is a block model. Block model consists of nodes which are clusters. So we have 4 clusters here, 4 nodes, and connections between these nodes. So you see all that I was talking about. So the blue one is connected with the yellow one. Pink one has arrows towards the yellow and the green one, and there is connection between green and the yellow one. This structure is now much easier to see what's going on in this network. So we clearly see that the yellow network, the yellow cluster is the central cluster, because all other clusters are connected to this one. So block modeling as an empirical procedure is based on the idea that units in a network can be grouped according to the extent to which they are equivalent, according to some meaningful definition of equivalence. I will say something about that. But before that, I have to introduce also blocks. Here on the left, I have a network presented by a matrix. It's a binary network because we have only zeros and ones. And below is the graph of this network, okay? And then again, I'm using a block modeling procedure. I obtain 3 clusters. And according to these 3 clusters, I permute rows and columns at the same time in such a way that I get the first cluster in those columns and rows, and then the second, and then the third. According to the clusters, I cut this relational matrix, right? And of them, if I have 3 clusters, I would get 9 blocks, I call. So each part of this is called a block. These are the diagonal blocks, and these are off-diagonal blocks. And here we see that here are ones and zeros, ones and zeros. Here are only zeros, ones and zeros, zeros, only zeros, ones and zeros, zeros, ones and zeros, ones and zeros. I will define a block model here. This is in a matrix form in such a way there will be a link between clusters if there are some ones, okay? And if it is only zeros, there will be 0. You see, so this is metric representation now of this block model. But what is the block? Block contains the links between units of 2 clusters. Now, equivalence. I said equivalence is important, that has to be defined before we go into the block modeling. The first definition was structural equivalence, and this equivalent means that if 2 units are structurally equivalent, if they are connected to the rest of the network in identical way. If units are regular structurally equivalent, we can get only 2 types of blocks: null block, or one covered block, or complete block, okay? These are diagonal blocks. Usually the diagonal, it's not an important thing. So also this is null block and this is complete block, okay? So if there is a structure equivalency, then I have only these two types of blocks, null and complete. There were many attempts to generalize structure equivalence because it is quite stringent. And one definition is regular equivalence, where units are regular equivalent if they link in equivalent ways to the units that are also equivalent. So maybe this definition sounds strange, but let me give you an example. If we have a hospital, we have patients and we have doctors. For instance, patients are assigned to a doctor. This is my relation here, right? So what is structural equivalent? Two units are structural equivalent. So patients are structural if those ones that are connected to only a particular doctor, okay? But regular equivalence means that two patients are regular equivalent if they are connected to one of the class of regular equivalency. So in this case, we would get two clusters, one of the patients and one of the doctors. In this case, we would get two types of blocks, null block and regular block. Regular block means that in each row, there is at least 1, 1, and in each column, there is at least 1, 1. This is regular block. And then when we were studying this block modeling in time, we came to the point that we see that there are many other possible types of blocks. We call them also ideal blocks. And there are still coming new ones because you can define them according to the problem that you are solving. And according to the problem, you choose which ideal blocks are important for my problem. And these ideal blocks define an equivalency. So this is generalized equivalency. Now, how to establish a block model? So actually, block modeling is a special case of clustering problem that we saw before. And here we have to define the criterion function appropriately. So for example, the criterion function, is described here, but I will present a little bit in an example so that you will understand what's about. For example, we have a partition into two clusters, and because we have two clusters, we obtain 4 blocks, and these are 4 empirical blocks. For each empirical block, this is for structural equivalency, where only 2 types of ideal blocks are present, null and complete, right? For each empirical block, we choose the closest ideal block. This would be the complete block. For this would be a null block. For this would be complete. For this would be null, okay? And then we compare each empirical block to its ideal block and look if there are some inconsistencies. So this one and this one are equal, so there are no inconsistencies. This one and this one, here is one inconsistency. Here is also one inconsistency. And here are 2 inconsistencies. If we sum up the number of consistencies, that's the value of the criterion function. So this is how the criterion function is defined. So, and this is actually described with this formula, which looks a little bit strange, well, tough. We constructed also these dissimilarities also for other types of blocks, not only for structure equivalency. And to minimize this criterion function, we used the reallocation algorithm, but also some others can be used. So this was just a very brief overview of the block modeling. We wrote 3 books about it. The first one was on generalized block modeling, and the last one is about new approaches in block modeling. This was in 2020. And this one here has a chapter that I will speak about right now. So it is about clustering of attribute and network data. So suppose we have these two types of data, and we want to cluster similar units according to the variables, and we will treat that with the criterion function. But we would like to consider also the relation, the network data. The relation imposes constraints on the set of feasible clusterings here. And this is done like this. The set of feasible clustering consists of clusterings, where in each cluster of this clustering, each cluster induces a subnetwork of the selected type of connectedness. So the type of connectedness inside the cluster determines the set of feasible clusterings. So here we have 5 types of these feasible clusterings. For instance, in each cluster, the unit should be weakly connected or weakly connected with one center. Yeah, I will be short. Or strongly connected, or they have to form a clique, or there has to be a trail inside the cluster. What we did, we adapted the hierarchical agglomeration algorithm in such a way that we developed 4 strategies how to adjust the relationship between the two fused clusters. In each step of this algorithm, you fuse 2 clusters. And when you fuse 2 clusters, you shrink the relational matrix by 1 dimension. And so we have to adjust the relationship between the fused ones to all other clusters. And we got these 4 strategies, and tolerant is compatible with the first feasible, with the weak connectivity, leader with that having 1 center, strict with that trail, and 2-way strategy with the clique. It's interesting that strongly connected units are difficult to be done with this approach. In the original approach, the complete dissimilarity matrix is needed. That's why not too big networks can be analyzed. Therefore, fast algorithm was proposed so that, that we consider only those dissimilarity that have linked units. And usually these networks are sparse, and so the problem is much easier. The algorithm can be adapted for minimum, maximum, and average method. It's interesting that this approach that I shortly represented you is still the only one for directed networks. There are some approach for non-directed or symmetric networks. For instance, regionalization problem is such. There are some new approaches for that, but there is still place to make research on that direction. And all these algorithms are implemented in the program PIAC developed by Batagel and Marwa. So to conclude, so we have to take seriously what is exactly clustering problem. We have to properly define it, and also to find a proper solution for that concrete problem. I was talking about 2 such problems where you see that you have really to think and to propose a new approach for clustering. Some algorithms like as clustering with relational constraints can be used for very large data sets. And some of them not really. For instance, generalized block modeling can generalize there around 1,000 units, but have difficulties to. So also here is an open space for new developments. Thank you very much. We don't hear you. Rim?
Oh, okay. Yeah, I have a simple question to you. So when you have a network, the analysis there is no consider the direction, outbounding and incoming, the direction between the object, you know? Do you think
Because-
about that?
yeah. So these are network data. This is about. So we have direction. Yeah. If I say directed network means that I have the direction, the relationship between one unit to the other.
Okay, so when we have that kinds of criteria we calculate, we consider the incoming and outbounding direction, calculate about that, consider that.
Yeah.
Okay.
Yes, we do. Yes.
And do you have any question to the Anusa's, the presentation and topic? So we met Anusa and Lynne met together in the IFCS, Classification Society meeting. So all the interesting, focusing on the clustering and classification together. And also next speaker also do some related to clustering there. Do you have any question to the Anusa? No?
Yes, there is one question. It says, networks are frequently studied on different topologies and metric spaces. Can your clustering work here as well?
Sure. But it depends exactly to which one, which exactly you mean. As I was saying, you have to take seriously what exactly is the problem, and then you can adapt or develop a new one. So it has to be very precisely defined, not so vaguely. Yeah.
Thank you.
So when we calculate the criterion function, we can get what is the optimal number of a cluster. When every time when I have a clustering, there is a what number of clusters is this identity. So for me, and the within cluster variance is small, and the between is a very simple idea. But when you try to clustering, what kinds of more advanced criteria?
Yeah, Terim, this is quite a difficult question. So there are many attempts to find and approaches how to define the most appropriate number of clusters, right?
Yeah.
A very simple one is that first you do hierarchical clustering. You do the dendrogram, and then you see where the jumps are very high, and that suggests the number of clusters. But there are many, many more sophisticated ways of doing it. Some algorithms even have implemented a procedure of, for instance, stochastic block modeling procedures. Now, they have already implemented ways of defining the number of clusters.
I see.
But the simplest one is just to look on the dendrogram.
Dendrogram. By the visualization, we decide the number of cluster right there.
Yeah.
Is there any other question to Anuška?
You have taken as 3 clusters and performance analysis you have shown. If we increases the cluster sizes, the number of cluster we increase, what is the impact on performance analysis for the given metrics?
Well, usually, but not for many approaches. If you increase the number of clusters, the criterion function is supposed to drop. But it can be that this drop is very, very little one. Therefore, if you have chosen the wrong number of clusters in the partition, then it can happen that the solution is actually less appropriate. So what Terim was pointing out, it's very important to try to figure out the right number of clusters. Sometimes also the problem suggests the number of clusters, right? So sometimes you simply, from the problem, you know exactly how many clusters you are looking for. So this is Well, this is a tough question, actually. To determine the number of the right number of clusters.
Yes.
Yeah.
When I have tried to data analysis for craniofacial data in the dental the data there, so I tried to make some clustering for the orthodontic correction the teeth, you know. So what kinds of abnormality I try to make a cluster, but what's the number is good for the cluster, you know. So I have a 5 and 7, and 7 I choose, you know, two criteria I fit in there. So after that, I discuss with the dentist. They agree that they are in their textbook. They make a 7 number of cluster they try, you know, diagnosis.
You know, so for instance, one possibility is that you simply try with many different number of clusters and look the criterion function, you know. And if the criterion function drops very much, you know, that means that you have chosen the right one. But it drops very little, you know, so you don't need to go further, you know. So that is also one possibility how to deal with it. Yeah, but you know, you see, in your case, you got empirically the number of 7, and then also theoretically the knowledge of your dentist knew that it should be. So this is wonderful. The best possible outcome.
Okay, your time is already so thank you for your presentation and joining us. And the next speaker is Professor Mihoko Minami from Keio University. So her topic is model for bycatch and clustering method for distribution, also classification, right? We are classification family. So why not give a big hands to her? Would you share your
share my slides? Okay.
yeah. Oh, okay. Can you pick up? Yeah.
It is all right. May I start? Okay. Thank you, Professor Lee, for introducing me. And hello everyone. I'm Mihoko Minami of Keio University. I'm very honored to present in this session, and I'm very grateful for Professor Lee for organizing this wonderful session. Okay. This is outline of my talk. First, let me introduce myself, then I'd like to talk about my research. About myself, I'm a professor at the Department of Mathematics, Keio University. I'm the only female faculty member in my department, and there will be none next academic year after I return next year. In my department, there are very few female students in my department. It is unfortunate that very few men in Japan major in science, especially mathematics. Increasing the number of women in science is now an important concern in Japan. I'm currently the director of Japanese Society of Applied Statistics. Also, I'm the chair of Special Committee for the Promotion of Diversity of Japan Statistical Society. I graduated from Ochanomizu University in 1982, majoring in mathematics. It is a national women's university. I have liked mathematics since primary school and enjoyed the student life and studying mathematics, but I never thought that I had the option of going on to graduate school when I graduated from university. After I received my bachelor's degree, I joined Nihon Univac, Japan Univac, and worked as a system engineer, developing statistical software and consulting on management science. Although the work is interesting, I gradually became interested in gaining more theoretical knowledge of numerical analysis, algorithm, and statistics. And as I had saved up enough money, I decided to go on to graduate school and choose to go to abroad. I entered the graduate course at the University of California, San Diego, and received master's degree in applied mathematics and PhD in statistics. I did not expect to get an academic job at all when I came back to Japan, but fortunately, I got a job as an assistant professor at Tokyo University of Science. I worked there for 4 years, then I moved to the Institute of Statistical Mathematics and worked there for 10 years as an associate professor. In 2009, I moved to the Department of Mathematics of Keio University and became a full professor. When I graduated from university, I never expected to become a researcher and professor. I became a researcher as I acted on my interest to learn more about what I was interested in. Okay, next, I would like to present some of my research I have done. My dissertation topic was mixed effects model for simultaneous response closed curve models. I worked on theoretical aspects of restricted maximal likelihood and other related topics. At Tokyo University of Science, in addition to continuing these studies, I conducted research on distribution theories such as multivariate Lagrange distributions. After I moved to Institute of Statistical Mathematics, I started to work on independent component analysis, which is a blind source separation technique. ICA was a topic that generated interest at that time. However, I began to think that I wanted to do research more related to real problems. When I visited the office of Clarity, who is a friend from my master course days, and found a wall full of interesting histograms. My friend Clarity received her PhD in oceanography after she received master's degree in statistics. She works at Inter-American Tropical Tuna Commission, which is a regional fisheries management organization responsible for the regional fisheries management, and management of tuna and tuna-like species, associated species, and their ecosystems throughout the Eastern Pacific Ocean. I'd like to introduce my joint research with Clarity from now on. Okay. The first research I present is models for bycatch. Bycatch is an unwanted marine creature that are caught in the net while fishing for another species. This plot is what I found in Claudia's office and felt remarkably interesting. There is substantial proportion of zeros, but also take exceptionally large numbers. We thought there must be two states. One is a perfect state in which bycatch never occur, for example, due to sharks not being around. And the other is imperfect state in which bycatch may occur. For imperfect state, we thought a negative binomial regression model, or NB model for short, would be appropriate because of the large variability relative to the mean. For this data, we consider the zero-inflated negative binomial regression model, or ZIMB model for short. This is ZIMB model is a two-stage regression model. We fit a logistic regression model for which state at set is in, and NB model for the number of bycatches to a set in the incomplete state. We also employed smoothing splines to express flexible spatial structures and other inferences. This table shows the values of generalized information criteria for several models. The smaller the GRC, the better the model fits the data. The model with smoothing had the smallest GRC value, which means this model fit the best to the data. This figure shows the estimated temporal trend in the standardized silky shark bycatch. Standardized means that bycatch was estimated in the same conditions all year. Lines in pink shows the estimates by ZIMB model with smoothing, and we find this estimate to be the most appropriate. The estimate by NB model are shown in green. These estimates overstate the decrease in shark bycatch. It is weird that the estimates are so different, so we theoretically figure out why this happened. First, we reproduced this phenomena with simulated data. The figure on the left depicts the estimate for the means of simulated NB data following the negative binomial regression with different means for class A and B. We produced ZIMB data, zero inflated data, by replacing a portion of positive values of NB data with zeros. The figures on the right shows the estimate for the means of ZIMB data by zero inflated data by Poisson regression and MB model. Despite replacing positive values with zero, the estimate by NB model for class A jumped up. We were able to replicate the overestimation of decline when NB model was applied to the zero inflated data. Before we explain the reason of overestimation, let me introduce the ZIMB model a little bit more. Probability function of NB model is as shown. It has size parameter theta. Probability function for ZIMB model is p plus 1 minus p times probability function of NB model for y equals 0 and 1 minus p times probability function of NB model when y is a positive numbers. ZIMB data can be regarded as thin data with an NB data replaced by 0 in a proportion of p. The reason for why NB model overestimate temporal trend when they are applied to thin data are as follows. The first, the size parameter estimate tend to be smaller than the true value. Then quotient estimate tend to have large absolute values with the same sign as the true values. As a result, the fitted values by the NB model become larger than the true values when the true values are large. Thus, the temporal trend is overestimated. At that time, negative binomial regression models were often used to analyze count data with large variance, and a paper using a negative binomial regression model to warn of the rapid decline in marine resources was attracting much attention. But some people argued that their results did not match their observations. We believe that The result of that paper may also overestimate the decline as our result indicates. Okay. And next topic is partition of the Eastern Pacific Ocean using regression tree and clustering for distributions. Okay. What we'd like to do is to find the partition of the Eastern Pacific Ocean based on distribution of yellowfin tuna body lengths so that the populations of each subgroup are as homogeneous as possible. There were 97 samples. Each sample contains about 50 tuna body length observations. In analysis, the data were aggregated by location into 5-degree and 5-degree cells so that samples were aggregated into 60 spatial cells. This figure shows histograms and the numbers of samples in 5-degree by 5-degree cells. Horizontal line shows the longitude and vertical line shows the latitude. So this area is the Eastern Pacific Oceans. It is observed that the shapes of histograms differ by cell or location, but there are some similarity between adjacent cells in some region. For example, the largest fish tended to be found in samples from the area circled in red, and the smallest fish tended to be found in samples from the area circled in blue. We want to find a partition of cells such that each region is homogeneous. Instead of histograms, we often use kernel density estimate to avoid problems associated with the choice of beam widths. Okay. We use the both method, regression tree and clustering. Regression tree is a divisive approach which starts from a set of all units and repeatedly subdivides sets using binary partitions defined by the values of an explanatory variable selected to provide the greatest decrease in impurity. On the other hand, hierarchical clustering is an agglomerative approach. Each unit starts in its own cluster, and the method repeatedly combines the two closest clusters by some metric. At the measure of distance between two distributions, we employed modified Jensen-Shannon divergence, or MJS divergence for short, which is the weighted sum of KL divergence from each distribution to the average distribution with size as weight. We also defined MJS divergence between two clusters as shown. We also defined the impurity of a cluster as a weighted sum of KL divergence from each distribution to the average distribution, and the impurity of partition as the sum of the impurities of all clusters. Okay. This slide shows the result by regression tree for tuna body length histograms. The figure on the left is the regression tree for histograms, and the figure on the right is the resulting partition of the Eastern Pacific Ocean with 4 subgroups. You can see the difference of distributions by subgroups. This slide is the result for density estimates. In fact, the partition is the same as that for histograms. Next, we present the result of analysis by clustering for distributions. For comparison, we performed clustering for distributions with 3 distances. Actually, it's not real distance, but we call it the distance. First one is MJS and Azimuth's distance and Clamel-von Mises type distance. We apply the method with and without adjacency constraint. The adjacency constraint is that only cells that share a latitude or longitude line are allowed to be merged. These are the resulting dendrograms of 5-degree cells based on tuner fork length distributions by 3 distant measures. Judging from the dendrogram, we thought that 3 or 4 might be a reasonable choice as the number of clusters. And this is a result by clustering with adjacency constraint. And the result by MJS has the characteristics most desired by people at IATTC. It captures the differences of distributions they observed, and the size of each group is not extremely different. In addition, we also propose the standardization method of MJS divergence in the process of hierarchical clustering and testing procedure of homogeneity of a cluster and hierarchical procedure to find a minimal homogeneous tree. And this figure is of clusters in the minimum homogeneous tree. This indicates that if we insist on homogeneity, there must be many subgroups or clusters. So we also propose the concept of near homogeneous homogeneity of cluster and a near homogeneous tree structure. This clustering method and program is now being used in analysis for other species at IATTC. Okay, this is the end of my talk on our research. I'm going to retire from Keio University next March. I'd like to spend the following year only doing research other than academic societies activities, although I will be back in teaching the year after next. So I'd like to have enough next year I can have time for my research, and these are my future research I'd like to work on. And these are short reference, and thank you for your attention.
Professor Mihoko, thank you for your good presentation and very practical. So it's very fruitful for us, you know. So when may I have a small question? When you have the regression tree, what kinds of method, cart or the fact or the random forest? There's so many machine learning method for the kinds of classification, right? So
Right.
what is it?
I think that the Carter type method. Yeah, Carter type
so,
method.
What kinds of regression tree method?
Regression
So-
tree and cart.
Cut. So
Yeah.
it is a
I use
diagnostic.
Okay, I use a different impurity measure.
And
Okay,
can I
impurity
know
measure is
the,
different.
can I know the classification result? You know, you classify with the model, and 1 and 1 classify, and 1 and 0 is wrong. So what is the classification result of your fitting?
Classification results.
So I mean that the error or the sensitivity or specificity in the epidemiology.
Okay.
Yeah.
Yeah. Actually, can I can I show you my slide again?
Okay.
Okay. Actually, I performed simulation experiment, and yeah, actually, I compared with the method with normalized mutual index and adjusted random index.
I see.
And the result shows that MJS had the best value in NMI and ARI. So
I see. That
I
is a
didn't have enough
criteria.
time to show my simulation experiments results.
I see. That
Mhm.
is why I asked you. And recently, I feeding the deep learning method, you know,
Mhm.
and the kernel discrimination also I try. So
Mhm,
there are
mhm.
various kinds of classification or the
Right.
regression tree.
You're
So,
right. Yeah, yeah. But they
So-
only actually but they are only 60 cells. They aren't so many.
I see.
Yeah, random first we thought that random forest and the other method, but they are only 60 cells. So
I see.
I don't think that
Good for your data. So our time is almost the only 4 minutes. Do you have any question among audience? 3 speakers are clustering related topic and a project. So it's a very good, we can share together, huh? So why not attend the IFCS meeting? Mihoko, did you attend there? Yeah, every
no,
IFCS
that's not true.
meeting. All the people interested about the clustering and classification. So Lynne and also the Anuška also we can meet
sounds
there.
great.
Yeah.
And
So
Dr.
if
Lee,
you
there
have
was a question for the last speaker. It says, how to perform Bayesian clustering in your case?
Actually, I tried it. Okay. I used the Chinese restaurant process for prior first, but it didn't work well because that it produced one big cluster and many smalls. So now I'm trying to find better prior for partition. Yeah. Yeah, that I think that Chinese restaurant process distribution is quite basic for prior for partition, but I think that it didn't work for my data well.
Thank you.
It is answer for your question.
Okay.
It's
Yeah. So we close our session now, and thank you for the 3 speakers, and let's have a meeting in a face-to-face meeting in the future. Okay. Yeah. Thank you.
Thank you very much.
Thank you for the audience.